Welcome back. So let us consider another set of worked examples. So we are treating these two together. It says show that the Taylor series expansion of e to the power of x and sine x about x equal to 0, which is of course the Maclaurin series. So that means all of these stories could have just been written as show that the Maclaurin series expansion of this and this instead of adding this about x equal to 0. So the Maclaurin series are the following: e to the power of x equals summation from k equal to 0 to infinity of x to the power of k divided by k factorial, and that of sine x will be summation from k equal to 0 to infinity of minus 1 to the power of k plus 1, then x to the power of 2k plus 1 divided by k plus 1 factorial. Okay, everything is just k. All right, so we want to get the solution to these. We take them one after the other. What is important to notice the fact that we use the Taylor series formula or the Maclaurin series formula or the Taylor series formula and set x not to 0, which is the same as the Maclaurin series formula. So we'll take them one after the other. For the first one, you see why these two are very interesting problems now. For the first one, we know that f of x is equal to e to the power of x, and we know that f prime of x is e to the power of x. I mean, the derivative of this doesn't change. And even if we get the nth derivative, it doesn't change. Still e to the power of x. So whatever derivative of e to the power of x that we have, so whatever order is going to be e to the power of x. So then, since we're interested in Maclaurin series, we're interested in what this is at x equal to 0. So the nth derivative of f at x equal to 0 will be e to the power of 0, which will be 1. Okay, so the nth derivative is 1. So no matter what the number n is. Okay, and now you will recall that the Maclaurin series, recall the Maclaurin series expression or expansion, Maclaurin series expansion for f of x is given by this expression, the summation from k equal to 0 to infinity, summation from k equal to 0 to infinity of what was that again? X to the power of k, we got that earlier, divided by k factorial, multiplying f naught, sorry, the nth derivative of this. So the kth, it should be kth derivative now since we're using k as our variable. The kth derivative of this evaluated as f equal to 0. Alright, so basically is given by this expression saying that f of x is equal to this. So then it will follow that f of x equals the summation. Okay, just write the summation. I said we'll simplify the summation as far as possible before we expand. If there's any need to expand, anyways. Of x to the power of k divided by k factorial. What is this expression? We found this expression already. That is f to the power and the nth derivative of x at x equal of f at x equals to 0 is 1. So So you can see it doesn't depend on n. So even if it was the kth derivative, it will still be 1. So whatever derivative it is, it will still be 1 at x equals to 0. So this will be multiplying 1. So basically, this is just equal to the expression. So we can already see that it is equal to what we were given, x to the power of k over k factorial. X to the power of k summation from k equal to 0 to infinity of x to the power of k over k factorial. It doesn't need any more thing. That is the end of the solution for the first part. We know this is equal to this. Okay, just by simplifying the summation. And we might be interested in expanding this further. If we expand this, for instance, now the expansion of it and this result in particular gives a very exciting observation. Don't forget, we still have another problem to solve. Okay, we will solve it. Okay, so we just want to make some observation here. It is the fact that f of x. This is saying that our f of x, which is e to the power of x, can be written as one. I mean, just this expansion. I'm just expanding these terms. When k is equal to 0, this will be x raised to the power 0, which is 1, divided by 1. So that's how I came about 1. Plus, when k is equal to 1, this will be x to the power of 1, divided by 1 factorial, that is just x. Plus, when k is equal to 2, that will be x squared over 2 factorial, that is x squared over 2. Plus, I mean, we've done something like this before, for which we obtained something like this. And we've examined the graph. So for this case now, and when k equals to 3, this will be x to the power 3 over 3 factorial, which is 6 plus that will be x to the power of 4 over 4 factorial. Let's write 2 factorials like that. It doesn't matter. So this is 2 factorial, this is 3 factorial plus x to the power of 5 over 5 factorial plus, this continues like that forever. All right. So this is the function. Now look at something that we've done before. In the past, we discussed the fact that the limit of e to the power of x minus 1 over x as x approaches 0 was equal to 1. Okay, we have seen different ways of evaluating this, that it is actually equal to 1 and all of that, blah, blah, blah. Now, because x is approaching 0, that means we should be interested in the expansion of this function. That is one usefulness of this Maclaurin series or Taylor series, if you like. Since x is approaching 0, and we know that around 0, we can take f of x to be equal to this series. Then, as x is approaching 0, whether from the right or from the left, we can represent this e to the power of x, okay, using this expression. And if we do that, then it should follow that normally, that is, we know this already. Okay, we just want to verify it. We know this is the expression for this limit, we know this is the result for this limit. Okay, but assuming we just want to get it around 0, where this is useful, where this expansion is useful for evaluating limits also, is the fact that when we take this divided by x as x approaches 0, since it is around 0, we can expand the function around 0. Expanding the function around 0 will give us this. For e to the power x to give us this expression. Then we know that around 0, this is going to be the limit as x approaches 0 of e to the power of x is now 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus blah 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 and so on, then minus 1, then divided by x, and we know that this will then be equal to the limits. So 1 minus 1, that will cancel this. Then when you divide all of these, each of these by x, this will be the limit as x approaches 0 of, so what we have left will just be x divided by x, which is 1, plus x squared divided by x, which is x over 2 factorial, plus x cubed divided by x, which is x squared over 3 factorial, plus the next one should be x to the power 4 divided by x, that will be x to the power 3 over 4 factorial. I mean, and that continues forever. But what is easy to observe here is the fact that all of the terms we have left will carry x. So as x approaches 0, we can say all of those things will be 0, 0, okay, 0, and whatever we have left will also be vanishing to 0. So at the end of the day, the only thing we have left will be the limit of this, which is 1. So this is going to give us 1 at the end of the day. So this is another way to actually confirm or verify, or if you like, say, evaluate the limit of this function. And this brings to bear one of the usefulness of this expansion and why it has to be done about a specific point, because it is around the point x equal to 0 that this is going to give us exactly what we have here. And so that is that about that. Let's move on, please. Let's move on to the second problem. This is not part of our problem, please. We just branched to see that this is actually a very useful expansion. All right. So for sin x, now let's deal with that of sin x. Um, we know that for this case, so let's say that is 2. Given that f of x equal to sin x, we need to get the derivative of f of x. So it's f prime of x equal to cos x. And from previous work, we have seen that this is just the same thing as sine x plus pi over 2. And we have also seen that by observing the patterns, we will have this nth derivative of x to be equal to the sine of x plus n pi over 2, similar to that of cos, just that this is sine. Okay, so that's basically what we need here. Then again, we will recall the formula. Okay, we recall this over there, but it's fine. We call the Maclaurin series expansion. Maclaurin series expansion of f of x is given by, so we write out the general formula for the Maclaurin series expansion, which is that f of x equals the summation from k equal to 0 to infinity of, what is that again? That is x to the power of k divided by k factorial multiplied by f to the nth, the kth derivative at x equal to 0. All right, so basically, if we evaluated this, we should evaluate this at f equal to 0. So the nth derivative at x equal to 0, that's will be equal to the sine of 0 plus n pi over 2. Okay, so this is just sine of n multiplying pi over 2. We've also observed a behavior of this before, but we'll come back to that. Let's move on first. We know this is sine of n pi over 2 since we substituted 0 here. And so going forward here, we can now say that therefore for this particular case, our f of x will be equal to the summation from k equal to 0 to infinity of x to the power of k divided by k factorial, then multiply by f of k. F of k will be sine of n multiplying pi over 2. So basically, this is what we have from this expansion. But now we can see that is not what we were given. So let's see if we can work towards that. Okay, towards the expression we were given. We were given that this should be equal to, or to show that this will be equal to -1 whole to the power of k plus 1, then x to the power of 2k plus 1, and divided by k plus 1 factorial. So this is the expression we have right there. So let's see, how do we establish this from all of the things we have here. So firstly, let us examine the behavior of this. We've done it before. Okay, we do know that. Okay, let's see it again now. So let's have sine. Let's clear this off and put in sine n pi over 2. So let's put in m there. Okay, m multiplying pi over 2. So this is times shift pi divided by 2. Then close this bracket. So let's evaluate what this will be. So let's calculate this. When m is going to start from 0. Okay, so when m is 0, so this is going to be 0. I mean, sine 0 is 0. Okay, that means when k is equal to 0, there will be nothing at all. We'll have no term because everything will become zero by the time we multiply by zero. All right. So we go to the next term when k is equal to one. Let's put in this. This will be one. When k is equal to two, we're going to have it to be zero again. So the next thing is when k is equal to three, what will happen? We have minus one. Let's calculate when k is equal to four. This will give us 0. Can you see now? That is telling us something that whenever our k is even, it is going to be 0. We've talked about this before. In the previous lesson, we did observe that this sign of n pi over 2 was actually going to be equal to 0 whenever n is even. So if n is even, it's going to be 0. And it will be plus or minus 1 whenever n is odd. So if n is odd, it will be plus or minus 1. Just want to write this. Just want to have enough space so that this can breathe. Okay, so it will be 0 when n is even. We've observed that before. And it will be plus or minus 1 when n is odd. That's what you have seen again with our calculator right now. So if it is 0 when n is even, then we know that this will not have any term when n is even. We are looking at the implication of this. It won't have any term when n is even. So that means that we don't have to bother with the even cases at all. That is when k is even. Sorry. So why am I writing n here, please? This should be k sine k since our fn, that is the nth derivative of sine n pi over 2. So this should be written as k. Okay, since we're using k here for our symbol, okay, instead of n. So please, that is important. All right, so when our k is even, we will not have any term at all. So we can forget about all of those. That means for our situation, k should only carry, sorry, k should only be, what is it now? K should only be odd. Now, we know that k should only be odd, but this summation still has to go from 0 to infinity, still has to go to infinity. So if it is going to go to infinity, then how can we manage this expression so that it always ignores the even terms? It always ignores the even terms because the even terms will always be 0. That means how can we manage this expression so that it only captures it only captures the values for when our power here and our whatever we have here is going to be odd. So that is why we now say, okay, if k is, how can we be sure that k will always be odd? Because whenever it is even, it is going to give us 0. How can we be sure that k is always odd? So that is, how can we ensure that this expression here is always odd, this expression here is always odd, and the expression here is always odd? But then we know if the expression here is odd, we know the implication of that, that our expression will just be plus or minus 1. So we'll also bother about how can this be plus or minus 1. We'll talk about that shortly. But now let's just think about this. Now we already know where we are going, so we just want to reason along with this, and this is it's a very interesting thing to do. So we know that our k should always be odd because when it is even, it's the particular term will vanish to 0. We still want to retain our summation sign, so this is the only way we can express sum to infinity. So now look at it. Our k will start at 0, it will go to 1, it will go to 2, go to 3, go to 4, go to 5. Now we want it to be that, now we know that when this expression here and this one here, when they are um, even, this whole thing, that of course that is when this one also will be even. When that happens, everything will be 0, so there will be no term. So we don't want that to happen, or we just want to ignore that, or we want to avoid that completely, so that whatever we are substituting from here, we know we have to still retain some expression here that will start from 0 and go to infinity. But we want it to be such that whatever that is, this expression here, this one here, and this one here will never be even. So it will always be odd. So how can we be sure of that? Now, one of the things you can think of normally is that, okay, what if we add 1 to this? If we add 1 to this, it will make it odd. If we add 1 to this also, it will make it odd. If we add 1 to this one, it will also make it odd. But we want something that will be consistent all through so that whatever expression we have here, since it's starting from 0 and it's going to infinity, we are certain that it will always give us a odd result here and a odd, sorry, a odd. It will always give us an odd result here and also give us an odd result here. And the best way to do that so that we capture all possible cases is to actually take this thing to be 2k plus 1. If we have 2k plus 1, for instance, so look at it now. We can also think of it as, we can also consider 2k minus 1. If we take 2k plus 1, when k is 0, this 2k plus 1, this expression here now, okay, when k is 0, this expression will be 1. When k is 1, this expression will be 2 times 1, which is 2 plus 1, it will be 3. When k is what else? When k is 2, it will be 2 times 2, which is 4 plus 1, it will be 5. So you can see that systematically, if we use this expression instead of k, we have systematically jumped all the even numbers. So we have jumped 2, we have jumped 4. And if we say this should be, if k is 4, for instance, um, what's the next one we should consider? 3. If k is 3, 2 times 3 is 6 plus 1, that will be 7. And if k is 4, that will be 9. And the next one will be 11, the next one will be 13 and 15, and so on and so forth. So if we use this expression, we have systematically jumped all of those cases where our k is even. So at the end of the day, we will only have the odd terms there. And now you can think of something. Now, what if we used 2k minus 1? That might work, except that when we have this expression here, when we have 0, 2 times 0 is 0. This will give us minus 1. Minus 1 is not a natural number. We know this only deals with natural case. So, natural numbers right here. So, that will not be a suitable thing to use. Okay. You can also think of, why can't we use something like, what of 4k plus 1? If you use 4k plus 1, the jump will be too much. For instance, when you are here, it will be 1. But when you are here, it will be 4 plus 1, which is 5. So it will have jumped 3. It will also jump 7 and 11 in that order. So 2k plus 1 is the expression to use. It ensures that we don't have to deal with even terms at all because they will all be 0. And it also ensures that, again, our k will start from 0. So since it is starting from 0, at the end of the day, by the time we use 2k plus 1 here, it will only be relevant for when k is, when the power of this is odd, and when this one also is odd. So if we go to the expression we have been asked to establish, we see that we have 2k plus 1 up there. So this is going to be 2k plus 1 right there. So we're going to use that expression for this. And if we do that, so let's examine what is going to happen now. Normally, this is meant to give us something like this. So let's examine how this is going to play out. So just experimenting with numbers. So let's say we start from k equals to 0, because we're going to infinity. Let's say we do x to the power of k normally over k factorial multiplied by sine k multiplying pi over 2. This is going to give us, when k equals to 0, is going to give us 0, I mean x raised to the power 0, which is 1, then sine 0, which is 0. So that will give us 0 plus. So when k is equal to 1, this will give us x, okay, to the power of 1 divided by 1 factorial, then plus when k is equal to 2, this will give us 0, plus when k is equal to 3, x raised to the power 3 over 3 factorial. This was sine pi over 2. This will become minus because it will be sine of 3 pi over 2, which will be minus. So they will keep alternating between positive and negative. So that's the idea. Then the next one would have been 0. Then the next one will be plus x to the power of 5 over 5 factorial plus what's the next one now? x to the power of 7, because this for the sixth one is will be 0 also, then plus x to the power of 7 over 7 factorial. That should be minus, so this will be negative. And the next one will be plus 0 again, plus x to the power of 9. That will be the next term, over 9 factorial, then plus another 0, then minus x to the power of 11 over 11 factorial, and plus, and so on and so forth. It continues like that. So we have seen already that the only things that will matter at the end of the day will be when this expression is 1 and this one is 1, when this expression is 3 and this one is 3, when this expression is 5 and this one is 5, when this expression is 7 and this one is 7, when this expression is 9 and this one is 9, when this expression is 11 and this one is 11. So that is the idea. So that means that now if we had used this result, for instance, if we had used k equal to 0 to infinity, and then x to the power of 2k plus 1 divided by 2k plus 1 factorial, then multiply by k, um, sine of this time around also, this will be 2k plus 1. Should be 2k plus 1. All of them will be changed to 2k plus 1. Then multiply by pi over 2. What will be the implication of this? This will mean that we will have successfully jumped all of this. So when k is equal to 0, this will be x to the power of 1 divided by 1 factorial. So that will be x. So just like x to the power of 1 here, divided by 1 factorial. Then the next one will be when k, this sign of pi over 2 will be positive. So the next one will be negative. And when k is equal to 1, that will give us 3. So this will have been minus x to the power of 3 over 3 factorial. The next one will be plus, and it will give us 5. And that will be x to the power of 5 over 5 factorial. And the next one will be negative. It will be x to the power of 7 over 7 factorial plus, and this will continue like that. So effectively, using this expression 2k plus 1 instead of k will help us ignore the zero term, so we don't have to bother about them. So we're effectively trying to say that this expression here will be equal to this expression, since we are very certain that whenever it is even, this sign part will make everything become 0, right? So that is what we are driving at here. So we use 2k plus 1 up here and also use 2k plus 1 down here. Then for this, we already know that by so doing, we have eliminated the points where it becomes 0. Once we have replaced k here by 2k plus 1, k here by 2k plus 1, k here by 2k plus 1, we have eliminated everywhere that it can become 0. Then the only thing is that it becomes 1 or minus 1. That is the only possibility. So we will have to cater for that as well. We have already catered for this, okay, the possibility of it being 0. So that is already catered for. The next thing is, in our expression, we have to take note of the fact that the signs will keep changing. So for the way the signs change, so look at it now. How do the signs change? We know that when our coefficient here, coefficient of pi over 2, when it is, what is it now? When our coefficient of pi over 2, for instance, this, what do we call it now? When our k is even, it was 0, we have taken care of that. But this keeps going from negative to positive, negative to positive, minus 1 to plus 1, minus 1 to plus 1. So can we have an expression that captures the essence of this portion? We know it is alternating between minus 1 and 1, minus 1 and 1. So can we have an expression that captures it instead? So that is why we now say, let us use, instead of this expression, we will now use minus 1 raised to the power of some expression, because we still have to make use of k. But now, how do we make use of k, or what k do we use? If we just use k, will that work? If we just use k, we always have, if we just use k now, let's say k equal to 0, this thing will be, for k equal to 0, it will be it will be equal to what do you call that now? It will be equal to 1 when k is equal to 0. So if we use this, it will be that the first term will carry positive sign, the next term will carry negative sign. That's when k is equal to 1. The next term will carry when k is equal to 2, it will carry positive. The next term will carry when k is equal to 3, it will carry what's that now? So this is starting from 0. So if it starts from 0, we should have this should work fine if it start from 0. So this should work fine. This should be minus 1. The first term, you can see the first term here. The first term is positive. The next term is negative. Yeah, the next term, the first term is what happens when k is equal to 0. When k is equal to 0, we have 2 multiplied by 0 plus 1. So this should work fine. We should have this expression here, which is x raised to the power 1 divided by 1 factorial, then multiplied by minus 1 raised to the power 0. Minus 1 raised to the power 0 will be 1. Then the next term will be this expression minus x cubed over 3 factorial, and that will give us the negative that we need, because this will be for when k is equal to 1. So if k is equal to 1, this will be minus 1. So that should work perfectly fine for us. So let us go ahead and write that out. So from all of these observations, so I've done a lot of rough work now. These are rough works. So let's just put them to one side. So but we just make this observation: sine of k into pi over 2 will be equal to 0 when when k is even, k in this case now, when k is even. We observed that before, and it will be equal to plus or minus 1 when k is odd. So therefore, we can say that our f of x, which is equal to the summation from k equal to 0 to infinity of what was the expression up there again? X to the power of k divided by k factorial multiplied by sine of k multiplying pi over 2 would be equal to the summation. Okay, we're still going from k equal to 0 to infinity. But this time around, we'll be having x to the power of 2k plus 1 divided by 2k plus 1 factorial. Then this will now go from uh, instead of our sign of this, we observe that it will be plus 1 or minus 1. So instead of that, we'll multiply it by minus 1 to the power of k. So we know that when k is equal to 0, this will be plus. When k is equal to 1, this will be minus. When k is equal to 2, it will be plus, and then it keeps changing like that, like that. So let's write this out properly. This is going to be equal to the summation from k equal to 0 to infinity of x to the power of 2k plus 1 divided by 2k plus 1 factorial, then multiplying minus 1 to the power of k. Okay, let's write the minus 1 to the power of k first, since it gives us the sign. The sign should come first, so let's just write that first. It's the same thing, but just for formality's sake. And we have x to the power of 2k plus 1 divided by 2k plus 1 factorial. And for a check, we'll see that if we try out this function, it is going to give us, for a check now, this is going to give us when k is equal to 0, we're going to have minus 1 to the power 0. Okay, it is 1. Then this will be x to the power of 1 divided by, this will be 1 factorial. Then when k is equal to 1, this will be minus 1 to the power 1, which is minus 1, and x to the power of 2k plus 1, that is 2 times 1 plus 1, that is 3 over 3 factorial. Then this will be plus minus 1 to the power of 2, then x to the power of 2k plus 1, which will be 5, divided by 5 factorial. Then plus the next one will be minus 1 to the power of 3. Then we're going to have x to the power of 7 over 7 factorial. Then plus minus 1 to the power of 4, x to the power of 9 over 9 factorial. And this continues like that, like that, and like that. So we see that this is just going to be equal to exactly what we need, because none of them will become 0. So effectively we've cleared up the 0, and we have also taken care of the signs. So this is going to be minus, this is minus 1 raised to the power 0, which is 1. So this is just effectively x plus, or this is minus, and this is going to be x to the power of 3. This is minus, so this will be minus x to the power 3 over 3 factorial. Then this will be plus x to the power 5 over 5 factorial. This will be minus, this will be minus x to the power 7 over 7 factorial, and this will be plus, that will be plus x to the power 9 over 9 factorial. If we consider the next one to be minus x to the power of 11 over 11 factorial, and so on and so forth forever. So this will be the expansion of the function sine x about the points x equal to 0. And so this expression captures perfectly what we need to obtain. Okay, so it's a better representation of this function. We could have stopped here, but we needed to just consider the property of this sine k pi over 2. We know how it dances around between minus 1 and 1 and 0, and so on and so forth. We eliminated, at this point, we've eliminated the possibility of having 0. Okay, because we have now changed the power here to 2k plus 1, which ensures that it always takes the odd value. And we have also what else now, eliminated, we've also taken care of the sign. We know the sign goes between minus 1 and 1, so this expression takes care of that. So effectively this expression is a replacement to this. Okay, and it is better, it is easier to deal with than the original expression we obtained directly from here. Okay, so now what is the meaning of all of this? Again, if you observe this, you see that sine 0 is still 0. Okay, so this is the expansion. Anyways, this is what we needed. So our solution should stop here. All right. So again, there's an interesting result from this. This is telling us that around x equals to 0, our f of x is equal to sine x is equal to this. So this is the value for sine x, okay, around x equals to 0. So we have seen that this works around x equals to 0. And we should recall, one of the interesting things about this is also the fact that one of the limits we've calculated before, we know before, was sine x over x as x approaches 0. We know that the limit of sine x over x as x approaches 0 was 1 from what we've done before. Again, this presents another opportunity, another unique way of getting this result. We can also see right now that indeed the limit of sine x over x as x approaches 0, since this is around 0, or we're interested in the behavior of sine x around 0, can be written as the limit as x approaches 0 of, we know sine x now to be x minus x cubed over 3 factorial minus x to the power 7 over 7 factorial. Sorry, that is plus, this plus x to the power 5 first, x to the power 5 over 5 factorial minus x to the power of 7 over 7 factorial plus blah blah blah. That continues forever. Then divided by x. So when this is divided by x, it is quite obvious that the limit as x approaches 0 for this dividing x, we will have 1 minus x squared over 3 factorial plus x to the power of 4 over 5 factorial minus x to the power of 6 over 7 factorial plus the next one will be something like x to the power of 8, okay, over 9 factorial, and the pattern continues like that forever. So because x approaches 0, every other term carries 0, and every other term that carries 0 will vanish to 0. So at the end of the day, this limit is just 1. And interesting result, interesting observation, that tells us that indeed this is one of the ways by which we can evaluate the limit of sine x over x as x approaches 0. Okay, so that's the end of this lesson. Quickly observe something, that what we obtained here, what we obtained here is that sine x is equal to this. Okay, this is the correct thing, please. This is correct. Oh. Everything we have done as explained is the absolute correct thing, is absolutely correct. Okay, this is the expansion of sine x around 0. This is the Maclaurin series expression for sine x as explained and derived. The expression in the question is different, which is wrong. So that is what it is, the question that is wrong, not our solution. So let's just correct that. Okay. So basically, that means the person who wrote out this question had copied the wrong thing. Okay. So it's not that we are wrong, please. So this is 2k plus 1, please. Yeah. So that is that about that for this lesson. Thank you for watching. We'll proceed from here in the next lesson.